So, we've talked about something of the ideal gas law. If we assume that if gas in a container is behaving like an ideal gas, and the key assumptions there are no force between gas of molecules, and the volume at gas of molecules is negligible. Especially we think about the container, when in the case we can assume we're dealing with something that kind of ideal, and we could apply the ideal gas law that the pressures times volume equal to number of molecules times the times ideal gas constant and times temperature measured in Kelvin. And it's that, well, real gas don't behave that, and especially as they approach their condensation point. Real gases aren't always. You can always make this assumption about them. And we can explore in this video how we might be able to adapt the real gas law, and we explore about van der Waals equations, same guy who come up with the idea of van der Waals forces. Saying, well, let's see if I can modify this P part over here and this phi part over here. So what is in the van der Waals? So let's give ourselves a container. I have container here, and I put some gas molecules in the container. So I've got some molecules here, and remember, that pressure equal to force per unit area, and the pressure is gonna from the pressure going from collision, the collision between the gas, the collision from the gas molecules bouncing off the walls of the container. Every time do that except a little bit of force on that area. And so you know that why the more temperature you have, these things are gonna be move around faster. You're gonna have more frequent collision. The more molecules you have, you're gonna have more thing to bounce around. And so and so those are things that if you have more of, you're gonna increase the pressure, especially if you're holding your volume constant. Now, this is assuming an ideal gas, but let's think about how things would change if we had a real gas where you do have, let's say, attractive force between them. Let's say van der Waals forces. So if you have attractive forces between the ideal gas movement about numbers of molecules, we will also assume that the molecules are not attracted to the walls of the container, which is always this case. Sometimes they are more attracted to the walls of the container, but let's assume that they are not attracted to the walls of the container. Well, the molecules of the middle, they are going to be attracting. We're going to assume that uniformly distributed about the volume. The one of the middle, they are going to be pulled in every direction. The one of the middle gonna every pull in direction. So there are gonna be really a significant net force, but that the one near the side of the container. So let's say molecules right over here. Let's say molecules right over here. Well, that gonna be have mass of the fellow of molecules are going to, in this case, be to its left, and so those are the ones that it's gonna be attracted to in this, and there's not gonna be too many or any in this case to the right of, and so it's going to have a net inward force Similarly, this one up here will have a net inward force, and closer in the center it's going to start dismissing a little bit, but you can see because of the attractive these things are more likely to maybe gravitate a little more towards in the current. Okay. These things are more likely maybe gravitated a little bit more towards the center than to ricochet of the side. They still will ricochet of the side. These things are buzzing around, super chaotic. You can't everywhere bouncing of the, but if there's some small attractive force, maybe a little bit more likely to more towards the center the two bounds of the walls of the container. It's reasonable. What if hold everything constant? What if hold everything constant? The real pressure less than ideal pressure. Because of this case, this attractive force, because of this case is about attractive force, but van der Waals said, well, can I quantify this difference? Where can we say the real pressure? We can say that the real pressure equal to ideal pressure minus something, and we try to figure out some expression that helps us into account this net force, especially from things that are closer to boundaries. It will for every s it's gonna be different depending on now they interest with in each other. So let's just put a little constant, in there with say, or it will for any of their molecules that just inward for it's going to be proportional to explicit density numbers divided volume. And number of molecules is going to be related to density again. So once you multiply the density again, so we put it density again. So and you can this notion that the real pressure could be equal to the ideal gas pressure minus A times N over V squared. All we can algebraically manipulate this, add this to the both sides of the equation, and we call that the real pressure. So we can manipulate this ideal pressure equals to real pressure plus A N per V squared. So after that we put to ideal gas law. We put that to ideal gas law. P sub R plus V sub R plus A N per V square plus V times V. And what we want to do with V, what we want to modify with V. So I'm gonna challenge assumption 2. We're gonna assume that these molecules and their will is not negligible, and so in this case gravitation hold everything constant. If you want the same pressure and everything else is constant, your real volume, in order to have the same pressure, is gonna be have the larger the real volume must be needed to greater than ideal volume. So we can write here volume of real gas is greater than volume of ideal gas. Why? Why that is to be greater? Well, in order to, if you want to make the volume greater, these things are gonna bump into each other a lot of more cause each other, taking a lot many space than you held assignment. So we can modify these to van der Waals equations. Real volume equal to volume of ideal plus Bn is this is a space. We can assume that we have a container and we have molecules in here. We have a volume of ideal gas and we have space here. So why the volume of the real gas is volume of ideal gas plus space. So we can algebraically more to phi sub I equal to phi r mean space bn. We can write down. So we can generate this to pv and rt. So we can put here pr plus a n per v square times vr mean bn equal to numbers of molecules, constant of ideal gas, and temperature measured Kelvin. This is van der Waals equations. This is why that van der Waals equation come from. And but once again, van der Waals equation is not perfect. That is typically given an expression to get a little bit. Van der Waals equation a good, but van der Waals equation is a good start.